Bismillahirrahmanirrahim. Hello dear students, I hope you are all fine. I welcome you all in class of Real Analysis 2. Our discussion is continue on functions of boundary variation. In the last lecture, I have discussed two theorems in previous two lectures that are related to functions of boundary variation. In today's lecture, I will discuss again a theorem related to functions of boundary variation, and this theorem is a very interesting theorem. Before starting to this theorem, firstly we will discuss what is Lipschitz condition and what is the definition of Lipschitz function. Function f from the closed interval ab to r, that is our function f is a real valued function. A function f is called real valued function if its range is set of real number r. So this is the real valued function over the closed interval ab. This function is said to satisfy Lipschitz condition over the closed interval ab if there exists a positive real number m such that the absolute difference of f of x1 minus f of x2 is less than or equal to m times absolute difference of the values x1 and x2. If a function f that satisfies this condition, that is the Lipschitz condition, is called Lipschitz function. So this inequality shows the Lipschitz condition, and the function f that satisfies this condition is called Lipschitz function. Now we move to theorem. Let f is a real valued function be a Lipschitz function over the closed interval ab. Suppose our function f is a Lipschitz function. Then we need to show that f is a function of bounded variation over the closed interval ab, but converse may not be true. Our theorem consists on two parts. In the first part, we will show that if our function f is Lipschitz function, then it is a function of bounded variation. And if our f is function of bounded variation, then it is not necessary in general that our function is Lipschitz function. So firstly, we show that if our function f is Lipschitz function, then it is function of bounded variation. Let P is the partition over the closed interval AB where the points of the partition are x0, x1, x2 up to so on. The first point x0 is A and the last point is B. Are in the order x0 is smaller than x1, x1 is smaller than x2 up to so on, smaller than xn. B a partition of the closed interval AB. Since f is a Lipschitz function over the closed interval AB, so by definition of the Lipschitz function, there will exist a positive real number m such that satisfies this condition. F of xr minus f of xr minus 1 less than or equal to m times xr minus x1, xr minus 1, where r is 1, 2, 3 up to so on n. Because in our partition there are the n plus 1 points, so that's why here we take this definition for r n points. We need to show that if f is a function of bounded variation, we need to show that f is a function of bounded variation. We know that function f is called function of bounded variation if its total variation is finite, and the total variation will be finite if its sum of total variation is bounded. This is possible when the total variation of f over the closed interval ab, that is this is the definition of total variation, or this is the formula of total variation of f denoted here v a to b f. This shows total variation of f over the closed interval ab, and this total variation is actually the supremum of this sum, and this sum is called the total sum of variation, or sum of total variation. So our target is to show that if this sum of variation is bounded, then f is function of bounded variation. So consider the sum k is equal to 1 to n f of x k minus f of x k minus 1. By expanding this sum, by putting k is equal to 1 here, this will become f of x1 minus f of x naught, plus by putting k is equal to 2 here, this will become f of x2 minus f of x1. By putting k is equal to 3, we get f of x3 minus f of x2, and lastly by putting k is equal to n here, this will become f of xn minus f of xn minus 1. Now we use the Lipschitz condition we have. What was the Lipschitz condition here? Lipschitz condition says that for every two values x1 and x0 belong to some closed interval AB, f of x1 minus f of x0 absolute will be less than equal to m time x1 minus x0, where m is some positive real number. Similarly, if we take point x2 and x1 belong to this closed interval, then again by definition of Lipschitz condition, we can write f of x2 minus f of x1 less than equal to m time x2 minus x1 absolute. Continuing this process, f of xn minus f of xn minus 1 absolute will be less than equal to m time xn minus xn minus 1. By adding all these expression, we have m time x1 minus x0 plus m time x2 minus x1 plus up to so on m time absolute xn minus 1. Whereas the left side of this expression is the sum of total variation, and that is actually here f of x1 minus f of x0 plus f of x2 minus f of x0 f of x1 up to so on. This absolute by using after applying Lipschitz condition that I will discuss now. This will be by taking m as a common here. We get x1 minus x0 absolute plus x2 minus x1 up to so on xn minus 1. Next, further, as we know that x absolute is equal to positive x if x is greater than equal to 0. In other words, if the number inside the absolute line is non-negative greater than equal to 0, then absolute value of x is equal to just plus x. Here consider x1 minus x0. As in our partition, I have defined that the points of the partitions are in this order: x1 is greater than x0, x2 is greater than x1 up to so on. So here x1 is greater than x0. When x1 is greater than x0, it means x1 minus x0 will be greater than 0. So if x1 minus x0 is greater than 0, then its absolute will be just equal to x1 minus x0. By this definition, we know that the absolute value of x will be just equal to x if inside the absolute the number is non-negative, that is greater than equal to 0. As here, number inside the absolute line x1 minus x0, this is greater than 0. So we can take it as x1 minus x0. So after removing absolute sign on every term, we have x1 minus x0 from first absolute, x2 minus x1 from second term, x3 minus x2 from the third term up to so on minus xn minus 1 plus xn. We can see that each term in this expression will be occurring two times, but with alternate sign, except the two terms, that is the first term x0 and xn. These two terms will appear in this sum only one time, because you can take notice here, x1 is here and x1 is also here. Similarly, x2 is appearing in the second term will also appear in the third term. So all the terms in this expression will be two times, except the 2 points x and x naught. So by cancelling out all the terms which are minus x1 plus x1, x2 minus x2, x3 minus x3. So we have remaining 2 terms, xn minus x naught. Xn is the last point of the partition P, that is B, and similarly x naught is the first point of the partition, that is A. Now our sum of total variation is less than equal to m times B minus A. And as A and B are the endpoints of the closed interval, so these are automatically finite numbers, and m by definition of Lipschitz condition is also a positive real number. So this numbers m to m b minus a is a finite real number. So sum of the total variation is bounded. Hence f is a function of bounded variation. Next we show that the converse of the theorem is not true in general. That is, we need an example that shows if f of x is a function of bounded variation, then it is not necessary that it is a Lipschitz function. Consider function f of x is equal to square root x. We can notice that f of x is a monotonically increasing function over the closed interval 0 to 1. We know that a function f is called monotonic increasing if its first derivative is greater than 0 over the interval. Here our f of x is square root x. The first derivative of the function is 1 by 2 square root x, where if we take for all x belong to the interval 0 to 1. So here our function f first derivative of the function is positive over this interval. That's why the function f of x is increasing over this interval, monotonic increasing function. In the previous lecture, we have discussed that if a function f is a monotonic function, then it is always a function of bounded variation. That is, if f is monotonic function, then f is function of bounded variation. So according to this theorem, this function f of x is function of bounded variation. Next we show that this function f of x is not a Lipschitz function. A function f is called Lipschitz function if there exists a positive real number m. If we find a positive real number m such that it satisfies the condition f of x1 minus f of x naught or f of x2, any 2 points can be chosen. This absolute should be less than equal to x1 minus x2. So suppose if we choose x1 equal to 0, no positive real number m can be found to satisfy the condition f of x1 minus f of x2 is less than equal to m times x2 minus x1 or x1 minus x2 for all x1, x2 belong to semi-open, semi-closed interval 0 to 1. That is, I want to say that Suppose here f of x is equal to square root x. This implies f of x1 that is equal to 0. This will become 0. So this Lipschitz condition will become f of x1 is 0 minus f of x2 absolute less than equal to m time your x1 is 0 here, 0 minus x2. Due to absolute, negative sign will be finished. This will become f of x2 less than equal to m time x2. Now f of x2 is square root x2 because your f of x is square root x. So this will become square root x2 less than equal to m time x2. This implies x2 over x2 and finally this become 1 over square root x2 less than equal to m. Now whether this inequality hold when your x2 approaches to 0? No. When your x2 approaches to 0, the left side will be unbounded. That is when x2 approaches to 0, then 1 over x2 will approach to infinity. So that's why we cannot find a positive real number m for which this quantity can be bound. That's why this function is a function of bounded variation, but this is not function of a this is not a Lipschitz function. I hope you have clear. I hope today lecture was helpful for you. Inshallah, in today lecture we will discuss a new topic. Take care. Allah Hafiz.